I'm going to give you a very high-level view of embedded systems, and for many of you, it might be a little bit too simple, because I guess most of you use embedded systems for work or research or teaching. So since I'm not very aware of the audience, so I made it a little bit simple, but in case so I would like it to be interactive, so you can ask questions and we can go into more detail, so when and if needed. So we'll talk about what embedded system is all about, and what are its major components, and then we'll talk about some of the design issues and trends and directions. So so all of you are currently holding an embedded system in your hand or in your pocket, which is a smartphone or a mobile phone. So communication is one major area where you see embedded system being used a lot. So that's not surprising. So in robotics, we see embedded system all the time, because so I'll formally define what embedded system is about. So then you will see that why I'm calling all this as embedded systems. So then you have all kinds of smart toys these days. So that's examples. Then on the other extreme, you have all the weapon systems of today, which are all embedded systems. Like this is an example of a cruise missile guidance system, but this is sort of an embedded system. Well, it is an embedded system, but I will kind of distinguish between some kind of embedded system from others in very shortly. Now your car, if you have a car, your car probably has more than 50 microprocessors. In a high-end car, it's more than 80 microprocessors, and they are connected by typical certain kinds of protocol buses, and then there is software running on them. So what they say is that most of the innovations of today's car, almost 75% of the innovation in today's car is in the embedded system in the car, and not in the mechanical components. Now if you take out all the stuff in your house, you will see lots of embedded systems: washing machine, refrigerator of today, your air conditioner, your dishwasher, even your set-top box that you use for your satellite or cable channels, and even these phones and everything. They're all examples of embedded system. So what is embedded system? So it's kind of like all of us understand what embedded system is, but it's hard to define it. So Marilyn Wolf, she defined it: any sort of device which includes a programmable computer, but itself is not intended to be a general purpose computer, right? So it's a computer that is embedded within some other system, and the main purpose of that system is not doing running web browser or doing scientific computation, things like that, but its purpose is different from computation, but the computation is what is needed for it to work properly. So basically the control and the interfacing to the actual system, mechanical or whatever system it is supposed to control. So another way of saying that is embedded system is computers inside a product. So and we saw ample examples of that. And normally, traditionally, we used to think of computing as personal computers, laptops, workstations, servers, mainframes, and all that stuff. But what we find today is that most common form of computing is not any of these. Most common form of computing is embedded in stuff around us, right? So even this microphone that I'm using is an embedded system. So computing systems that have all these components that make it work normally is the one that actually sells the most. So if you look at the processor or microcontrollers that go inside these embedded systems, have more cell than the normal your Pentium 4 or various variants of Pentium 4 or the PowerPC and things like that. So it's actually, I'll show you some of the statistics soon. And here is a list of embedded systems, and by now I have already mentioned it several times that there are all these equipments that are around us. They are all embedded systems, so I will not dwell on this further. So the question is, how many do we use? And an average middle class American home has 40 to 50 embedded processors in it, right? So and nowadays with the current situation, even in middle class or upper middle class Indians have the similar numbers. As I said, that modern cars have about 80 or more embedded processors, and they actually control everything from anti-lock brake to steering to window rolling down windows, locks and ignition and all various kinds of displays, music players and so on. But even our personal computers that you buy from the market also has embedded processors, because there are things such as your CD-ROM controller, your bus interface, your network card, even your keyboard and hard drive, and then graphic accelerator like GPUs and so on. So they are all sort of can be thought of as embedded processors. So so there are several types of embedded systems, and mostly we look at these as regular embedded systems and cyber physical systems, right? So cyber physical systems are the most common form of embedded systems that we see, and that has actually that has been brought into focus by NSF for last 10 years. That so when you look at embedded systems normally, and since this is a sensor and actuator workshop, so normally what you try to do with a system is that you want to control something, right? So when you control something, you actually can have two types of control: open loop control or closed loop control. And if you have open loop control, then you are basically not getting any feedback from the environment in which you are trying to do something, right? So open loop control are simple things, but whenever you have closed loop control, you have sensors and actuators in the system, right? And the sensors are the ones that tell you about your system, about the current state of your system through some measurements. And from those measurements, what you do is that you construct what is called a state estimation. You try to understand your system state. And when you estimate your state, then you know exactly what you have to do to change the state so that you are closer to where you want to be, because there is a control trajectory that you want to be in order to make things work. For example, if you are trying to do a let's say cruise control in your car, you have a target speed and a sensor tells you that this is the current speed, and you basically look at the difference and you try to figure out how I can bring down the difference so that the difference from the target speed and my current speed is 0. So you have to apply some throttle, and to apply the throttle you have to compute the what you want to send to your actuator. So that's what your system is doing. So that's a closed loop control. So so control systems are always necessarily made out of multiple sensors and actuators, as well as embedded controllers, which are either microcontrollers, which are very small microprocessors, or regular microprocessors in case the control computation is pretty expensive. And nowadays, as we'll mention afterwards, that lot of the sensors and actuators also has microcontrollers and processors for local control and local decision making and things like that. So control systems are a major part of embedded system. Now, there are embedded systems which are general purpose computing. For example, the phone that you use, smartphone, is actually an embedded system which has general purpose computing behavior, right? It's like, you run applications, you can actually run anything that you can run on a regular computer. Then there are special purpose embedded systems, for example, for signal processing. So you can have embedded systems in radar, in sonar, and video compression. This kind of stuff you do signal processing, and there also you need computing power and adequate microprocessors. And then also communication and networking. Also, like for example, this the wireless router you have at your home, or the router that you have at your office, they all have microprocessors in them, and they are actually basically embedded systems. So and then nowadays with the internet telephony and so on, you have those also as parts of your embedded system. So cyber physical system is actually one of the major areas of embedded system today. And the idea there is that you have a physical system and you have a control system. And the physical system, for example, the power system. So you have generators, and you have various kinds of components such as transformers. You have the transmission lines, and you have power being generated. They are carried over transmission line. They are going to go into certain substations, and in the substations they are going to be actually stepped down or stepped up depending on what you are doing, and then moved into various directions. And then you have eventually these transmission lines will come to a distribution substation, and then from the distribution substation you will have distribution lines to various localities and so on, right? So in this kind of a system, there are multiple different problems, right? So this is a huge cyber physical system. Why it is a cyber physical system? Because the physical part of this system, that is power generation, power transmission, these are only describable by differential equations. They are physics based systems, right? So differential equations kind of models their behavior. So there is no computing being done when power is being transmitted from one end of the transmission line to the other. However, you have to make sure that this entire system is in a stable state, because if it goes out of a stable state, then you will have various kind of things. You have voltage collapse, you will have cascading failures, you will have various kinds of problems, like the one that happened if you remember in July of 2012. There was a huge power crisis that moved from the northern grid to the northeastern grid to the eastern grid, and 600 million people were without power. In 2003, that similar thing happened in New York, and all of these things is because the stability of the control trajectory of this entire large system, a distributed, geographically distributed physical system, was out of the stable trajectory, and it collapsed. So in order to keep this entire system in trajectory, you have to apply control, and you have to apply control by knowing the current state of the system. So state estimation is what is done by all the control centers. So you will have Calcutta has a load dispatch center for eastern region. For northern region, the load dispatch center is in New Delhi, and things like that. So these dispatch centers, they are actually main control centers where all the sensors send their data, and this data is aggregated in order to compute the current state of the system. So this is for per regional grid has its own state being estimated, and then accordingly control is done. So currently this control is not closed loop, it's a human in the middle closed loop, right? So a human engineer sits at the control center. If you ever visit a control center, you will see a lot of displays, and they are looking at it. So all the sensor data is being converted into knowledge and being displayed on these displays, and these engineers then can make a decision that, oh, we have to do a load shedding here, or we have to do a generation shedding here, or we have to call this guy and say that their reactive power is not being supported, and they have to do something, or I have to start pumping in some power here, things like that. So normally you would like eventually in a smart grid that all of these things will be done automatically in a closed loop, but right now we don't do that. But this is a physical system that is being controlled by a computational system, and this computational system is actually also distributed. So there are local controllers in a power system, as well as these control center specific controllers, and these controllers keep the system under control. So similarly, if you look at the power generation center, it itself is a cyber physical system. The generator itself has to be under control so that it doesn't run away with weird speed, and then your generated power is no longer 50 hertz, and you will be in trouble, right? So there has to be sensors sending data to a controller. Controller will send actuation signals to make sure that you decrease the speed at which the rotator the turbine is rotating, and things like that. So there are two kinds of automations here. One is called product automation, another is called production automation. So what I just described is kind of production automation. Now inside a car, what you see is more like a product automation, where you have various things that are what we call nowadays drive by wire, right? So early days everything was mechanical, even brake was mechanical. Now everything is done electronically. By when you press the brake, you are basically telling a sensor that I want to stop, and then that information is carried to a computer or a microprocessor, and that information is then depending on what the current speed and so on, the brake will be applied accordingly, and the actuation signal will go to the brake, and then accordingly things will happen. So same thing with fly by wire in case of avionics or aeroplane. So these are kind of things that happens in embedded system. So if you look at computer science today, most of the people except few would be more working in this domain of computer science than traditional domain of computer science, the embedded systems. And also embedded system is interdisciplinary, right? So when we work with the smart grid people, we are looking and talking to people in electrical engineering, we are talking to people in power engineering specifically, and then we are talking to people in computer engineering, computer science, electronics, and so on. So in mechatronics, you are talking about mechanical engineering people talking to computer people, and so on. So as I already mentioned, the typical cyber physical embedded systems are designed to be observed through sensors and control something through actuators. And so I gave a lot of examples, but a simpler example is air condition senses the room temperature and then applies control on the speed of the air that comes in, or by setting the thermostat, so it changes the temperature. So what does what happens in the system architecture of the embedded system, right? So here, let's say this is your board that is your computation is happening here. So you have to have a processor to do the computation, and then you have sensor interface, you have actuator interface, which here is called observe and control. And then you probably need some memory, and of course you need connection to disk and other things. But this is a very simplified diagram. And then in this simple case, you have a temperature sensor. Maybe this is an alarm system where when the temperature goes above a certain threshold, you want to sound an alarm, or you want to turn on a light, or you want to turn on a motor to do something when the temperature is going to certain level. So this is sort of like an example computation being done in an embedded system. So embedded systems has two parts, mostly two parts, which is hardware and software, right? So the hardware part is through microprocessors, microcontrollers, memory, system bus, and then you have the I/O interfaces. I/O interfaces connect you to sensors and actuators, and the processors in embedded space are quite different from the processors that you buy for your desktop or servers or your laptops. And oftentimes these processors could be very simple if your embedded system is supposed to do very simple computation, whereas if your embedded system is supposed to do a large amount of computation like a power estimation in a grid, then you are going to have almost general purpose or better than general purpose machines. So but in general, now embedded systems are very cost sensitive, right? So you have to always look at, you don't throw in a microprocessor if you don't need it, because you are going to, usually embedded systems are also mass manufactured, right? So except examples of power system control or controlling a chemical process or something where you are uniquely building a control system, but most embedded systems are actually going to be built in scale. So therefore you don't want to, like, even 50 cents per processor, if you can save, you want to save that because you are going to make millions of them, and then even so it's very cost sensitive. So oftentimes you actually have to go for the lower clock speed processors because you don't want to go and throw in a Pentium for when you don't need it. And oftentimes they are integrated with memory, and because you need high speed, and also you want only one component. I/O devices are usually connected, so usually they would have analog to digital, digital to analog, and then you have other things like pulse width modulator, or you can have interface to a very specific kind of bus like a CAN bus, and so like control area network bus and so on. Now another thing that often is needed in these processors is that they are built for higher environment spec. So oftentimes these embedded systems are placed in environment which is pretty rough, right? So for example, if you look at the substations, our substation for our internal grid, they are always under, like, during summer they are at under 50 degrees temperature, during winter they are at 0 degree temperature. So these wide variations and all should not hamper the working of these processors, and therefore we have to have a much rugged version of the processor. So you don't keep these things inside a spatially temperature controlled environment like we do in our servers. Now so microcontrollers are actually very simple microprocessors. So the microprocessors, usually microcontrollers are 8-bit or 16-bit microprocessors with probably don't even have a floating point unit, and which is going to make the microprocessor very power hungry. So you want to conserve battery life. Many times these things are actually battery operated devices in which you are putting the embedded system. So you want to have a very simple processor with very little with adequate functionality, but not more than needed functionality. So microcontrollers are built and sold in in millions and millions. And so if you look at the market survey of recent market survey, then you would see that in 2014 the standard PC server etc. Was 64% of the market, whereas cell phone and tablet, which are actually not microcontrollers but microprocessors, are about 31%, but it's slated to go up very quickly. So in 2018 they are projecting that it will be even more, like about 41% in this market. Now this is just the computational, this is not even considering the microcontrollers that go into embedded system. This is just the cell phones versus regular computation. Now if you look at this one, you will see that here we are talking about when you bring in all those other things, then we see that 50%. Now this is actually not in number, this is in the dollar price, right? So numbers will be much less for this 50%, because these processors, each processor that goes into an Intel processor or AMD processor that goes into a server is $600,000, right, each. Whereas we are talking about 4-bit, 8-bit microcontrollers, we are talking about cents, right? So the numbers, this is not a numbers chart, but this is more like the amount of trade volume chart. But even there also we see that about 40 some billion dollars in 2016 is supposed to be all those other things, and the other 50% is PC. So that gives you an idea about where it all stands. And then if you go by the various manufacturers, it's about this number. Now these are from very different places, so the numbers vary a little bit, but you get the basic idea where where it all stands. So this is the processor, again mobile phone versus PC versus tablet. You see that over last 3 years in 2014, the increase in the mobile phone and tablet processors, whereas the PC market is actually going down, right? So now why are there so many microcontrollers in the world? And so I got this from a colleague that there are more insects than any other species in the world, right? So the green is the insects, and then rest of it's like exponentially different. So it's very similar. So types of microprocessors, so you have computational microprocessors, which we normally put into workstations and PCs and high-end portable devices. They are 32 to 64-bit. Normally now 64-bit is the most common one. And examples would be the ones you're familiar with, like Pentium class processors, and then the PowerPC architecture, RISC, that's mostly from HP, Sun Spark, and so on and so forth. Now, general purpose embedded processors, 32-bit data path, they are also pretty common these days. So ARM is the leading company that makes that basically designs this. They don't manufacture them. Then you have MIPS, you have PowerPC, and then also old x86, 68K, and so on. So one time I was in Germany, and I suddenly bumped into one of my colleagues from Intel when I worked in Intel many years ago, and I was surprised to see him, and he said that he came to meet Volkswagen. And I said, why are you meeting Volkswagen? Apparently they use x86 processors for their car entertainment system, right? So you don't think that Intel processors are being used in cars, but actually they are being used in cars. So then you have microcontrollers, which are 4, 8, or 16-bit data path. So usually pretty compact, and they're often very, very low cost, and they're high volume devices. Now those embedded general purpose ones, they are not necessarily very low cost. For example, ARM, if you use a most recent ARM processor in your system on chip, then you are going to pay quite a bit of money, like about probably $15-20 per piece that you sell to ARM for that design. Then you can also have domain specific processors. So data path will vary based on the specific application that you are going to use it for. So examples would be network processors, security processors, graphic processors, and so on. So security processor is something that is a very new thing. So when you want to have a firewall, for example, or when you want to have a specific security equipment that is going to actually look at the packets that are going into your system or going out of your system for very specific security threats. Nowadays they have this very domain specific hardware that are being sold by various companies, including Cisco, and these processors are very, very specific to the algorithms that we use to actually look at this very fastly the very fast coming packets, and very quickly do some observations on them to and then keep statistics of them and so on. So these are called cyber irons. So now I want to show two different graphs. The first graph is between 1990 and 2000, and the number of the units of monthly units that of this kind of processors that are sold. Now you will see that in between 90 and 2000 the amount of automation has increased quite a bit, right? So this you see that all the different processors except 4-bit microprocessors are actually on the rise, but biggest rise was on 8-bit microcontrollers, right? So this is a different time. Now if you look at this, so if you look at last couple of years, so you see that there is a decrease. Here the graph is from the right to left for each of these different categories. So if you look at this 8-bit microprocessor, their market share has been decreasing, and the 16-bit processor market share is also decreasing, but not so much. And then the 32-bit processors are increasing, and then 64-bit processor is also kind of stable. So you see that the trend is kind of more going towards 32 and 16-bit, and not so much into the 8-bit processor. So microcontrollers are not so much needed today. Then also there is this programmable logic component. So there is also a trend that you want to have some programmable logic in your computation board in your embedded system. So which basically means FPGAs, field programmable gate arrays. And this is from a survey of last year. And it seems like the number of the usage of field programmable gate arrays has decreased in the last few years, and at some point it was quite large, which was in 2010, and that the reason is probably because the amount of the need for reprogrammability depends on how you are going to use it, and if the customer wants to reprogram the hardware component of your embedded system, and it seems like that's not the growing trend. So this is another one of those graphs, so let's not worry about it. Now what are the common characteristics of embedded systems? So the one common characteristic is normally you want to do a single function, single goal that you want to do, and so it's usually you want to get a single function out of this embedded system. So even in cars, right? So you have the music entertainment system is a different embedded system compared to your brake system and compared to your air condition system and your acceleration system or your cruise control system. They are all. That's why you have so many microprocessors. You could have taken a much larger microprocessor, much more powerful processor, and integrated all these functions, but that's not normally done. The reason is that it gives you a much better fault tolerance. So for example, if your air condition unit is connected, is in the same processor as your brake, and then if your brake doesn't, your air conditioner doesn't work, maybe your brake will also fail, and that's not good, right? So you want to separate them. So normally these embedded systems are tightly constrained in the sense that the cost has to be very, very low, the power consumption has to be very low, and it has to be the form factor must be small, so it fits in various places, and it has to be fast, and it has to have fast enough to actually provide the service that you are requiring it for. And then it is reactive and real time. So which means that unlike desktop computers where you actually turn it off and go home, or you can actually let Microsoft download its latest patch while all your work stops, and it reboots it 3 times before it finishes patching. You cannot do that in this kind of systems, right? So you can do it when you are in the shop, like if you take your car to a car shop, they will connect it to their computer system and do diagnostics, maybe download a new firmware onto your car. But normally when you are running, it has to be running and reacting all the time, because it doesn't know when you are going to press the brake or when you are going to press the accelerator, and therefore it has to be reactive. And then many of the functions in embedded systems are real time, and by real time we mean that the response to an action that is caught by your sensor has to be time bounded, right? So otherwise, if you press the brake and it takes 5 seconds, then you are dead, right? So you have to be, it has to be, a couple of milliseconds before the actuation happens. So real time is one of the biggest issue in embedded system, biggest characteristic of embedded system. So as I said that, oftentimes it is single function or maybe more functions may be included. Deadline constraint means basically real time, as I said. Resource challenged, as I said, that oftentimes you want to keep the form factor low, and therefore you cannot even put too much of memory, right? So your form factor has to be small, and then power efficient. So many times you are working on battery, and then it has to be manufacturable in scale, right? So it has to be, it cannot be too customized. So the yield of these things has to be large. So and then the biggest thing about embedded system is that the design focus is not computing. Design focus is the application. Computing is just a just a means to get to an end, right? So when you think about computers in desktop and servers, their computation is the main, right? So here the computation is there just to make sure that you can do your stuff, whatever it is. And in this case, it shows an example of a farmer that relies on high-tech gadgets for farming, and embedded system is the one that makes it makes this thing. So when we design embedded systems, we have to consider several things, right? So one thing is functionality, right? So we say, okay, this I want to control this system. Here is how I am getting the sensor inputs, and here is how I am going to be actuating certain things, and then this is what my computation is, right? So if I am going to do a PI control, then I will do certain types of computation. If I do some other kinds of control, I'll do that kind of computation. So that's functionality. Then you have the in terms of performance, right? So performance include efficiency, throughput, latency, but it also requires you to do real time for certain applications. But all these things you are given as a requirement, but with a design constraint. You are told that all this has to be achieved with the following constraints. So design constraints is a big part of embedded system design. So we already looked at some of these. So but design constraints may be given to you in a very quantitative manner. For example, you might be told what is the form factor that you have to achieve, and sometimes the form factor is also associated with the power dissipation, for example, right? So if your system gets heated up, then you cannot your package might melt, right? So you have to have the form factor associated with the heat dissipation requirements. You also have to worry about hardening the system so that it can be placed in a harsh environment. So including vibration, shock, and all other kind of stuff. Then there could be interference. If you are putting your embedded system in a substation, there is high amount of electromagnetic interference. You have to be able to shield the system so that the interference is little. You may have to be able to withstand water, corrosion, all that stuff. Then safety criticality. So not all embedded systems are safety critical, but flight guidance system or the system that goes into your car for anti-lock brake or for cruise control, this must be done in such a way so that it is correct with 99.999% guarantee, because you cannot have this kind of systems malfunction, because human lives and properties are under danger. So these are called safety critical systems. So if your embedded system is safety critical, then you have to worry about safety, making sure that it is up to that standard of safety criticality. So if you look at the industry today, for example, for any embedded system that goes into an aeroplane has to be certified, and there are standards in the industry, DO 178C, and these standards have to be maintained in order for it to actually be certified to be airworthy, right? So that's why when you look at the companies like Boeing and Airbus, usually when they manufacture a plane like A380, for example, they have to make sure that it works for 30 years, because to get certified, like you cannot patch like Microsoft. To have a patch there, it has to be certified by the corresponding authorities, and if you cannot certify it, you cannot put it in. Therefore, changing is not an option. So these kind of systems are safety critical, and once it has it has to be put in public service, it has to be certified by special certification authority about how it was manufactured, what process it followed, and show the details of the process it was followed to validate the correctness of the software and hardware. And as I said, that there is an extreme cost sensitivity, because we are manufacturing in huge scale. Then the biggest problem, so if you go and ask any company that develops embedded systems for large applications and safety critical applications, what is the costliest part of your design, right? So they will always say validation, right? So usually the anecdote is that about 70% of the cost of designing and manufacturing a system is in validation or verification, right? So the question that I want to answer in verification is, does it really work? And what it means by does it really work is that given a specification, does it work according to specification? But who knows if the specification is correct? So that's usually the validation part, right? So you have to also prove that your specification is correct. For example, if your aeroplane has this properties, does that mean that it will be actually flying, right? So you have to basically validate the specification, and then once you have implemented it, you have to prove that the implementation meets the specification. So that's the verification part. And then you have real-time properties. So not all the responses has to be real-time, but certain responses have to be real-time. And so how do you prove that, or how do you test that the real-time properties are being met? So if you know the story about the Mars rovers. So Mars rovers, NASA sent this back in late 1990s, and then it stopped working after some days. And the reason why it stopped working is because there was a problem called priority inversion problem, right? So if you know about real-time scheduling, there is so this is a priority-based scheduling, and then something got because of the dynamic priority assignment, somebody's priority got changed, and then it could not bring up the system. And the priority reversal problem, or the problem that happened, although this device was tested, this system was tested in the laboratory long time, but since this happened in a very specific case, and that specific case was not reproduced in the laboratory, they could not imagine this could happen, and the whole millions of dollars mission was completely useless because of this priority inversion bug that came up. There are many other examples like that. So testing for real-time characteristics is very, very difficult. So so then the other question is that suppose you have your system has 100 sensors, right? Now not all sensors, some of the sensors might be redundant, but many sensors are such that if you lose one of them, you cannot estimate the state of the system. You cannot tell what is going on in the system, and this is called loss of observability. You cannot observe your system to its fullest. So if you lose observability, you cannot control the system because you don't know the state of the system. So the question is, when you design your sensor interfaces and choose your sensors and so on, question is, how do you make sure that your system is always going to be observable? How much redundancy you have to put into the system? Then controllability is similar issue, right? If the actuation doesn't work, then you lose controllability. And then you have to choose a development platform, because in most cases you don't design the embedded system on the system itself, because you usually create a sort of like a SDK or software development kit on which you have to develop it, right? Because normally if you develop in the real device, that it might be actually very expensive, or it may not be even practicable to actually do this. So then the other thing is the optimizing the design metrics, right? What are your design metrics that you are optimizing for? So common metrics that people do optimize for is normally big one is a cost, as we discussed before. So unit cost as well as non-recurring cost, and then the non-recurring cost includes the software, because software is a non-recurring cost. Because once you develop the software, you can put it many copies as you want. The size, obviously performance, power, and the flexibility. How quickly you can, some systems might require you to reprogram the system, so you need flexibility and so on. Then the other thing that is very important for especially consumer space embedded systems, not so much for even actually for safety critical embedded systems, this is important. So I don't know if you have heard of F-22, right? So F-16 is actually the fighter jets that the Pakistanis got and we didn't get, and all that stuff, right? And now currently US is manufacturing F-35, but in the middle there was F-22. So F-22 was manufactured by Lockheed Martin, which is a company that is a special defense contractor. And what happened is that it ran the project cost and time went above the stipulated time by 5 or more years, right? So at some point the US Congress said that let's end this program. So after so many billions of dollars spent on F-22, it was never made into a product, right? So you cannot buy F-22 from Lockheed. You have to buy now F-35 if they allow you. But so time is very important, right? So because by that time the F-35 was being developed in parallel, and F-35 got into a maturity stage when F-22 was no longer needed. So all this stuff was happening. But a bigger interesting example is that many years ago Intel was developing its first integrated microprocessor called so it was being developed in Israel, and it was supposed to first time integrate the microprocessor, the memory, and the chipset together in one chip, right? So this was in year 2000. And this was supposed to cut the cost, because you don't have to make 3 chips. You integrate them in one chip, and this is the time when system on chip was not so common to do. And they had this only problem they had is that they decided to use a memory interface that called rhombus, and this memory interface was actually was being designed by a single company. And for some reason the Intel vice president thought that this is a good idea to actually have rhombus memory on this. So at this point, this was supposed to be a sub $1,000 laptop, and the target audience was back to school kids in September when US schools open. So in May they realized that this rhombus is not working, and therefore they have to create a new interface for regular SD, regular DRAM. So therefore at this point they realized if they want to do this, they will miss the September deadline to actually bring the product to the market. So they completely cancelled after several billions of dollars spent on this project. They completely cancelled this project, right? So time to market window is very, very important, and we'll see a graph about this soon. Actually here it is. So time to market is a very important design metric for embedded system. So normally, so this is basically showing is that if you introduce too early some product, then your revenue is low. If you are at the right moment, then your revenue is good. But if you are beyond some time, then your revenue is again down. And then so depending on what kind of product it is, the time to market is different. Like for example, nowadays in cell phones, it seems like it's about 6 months before which you have to come up with a new product. Otherwise, you are going to miss people buying the next version of your product. So, but for cars, it's usually a couple of years, right? So it depends. And then if you delay the entry into the market, so this basically shows that if you are doing an on-time entry, and then you reach a peak, and then you go, start gradually wane, and then if you are delayed by a little bit, then you reach peak at a much lower peak because your growth rate is kind of similar, and then your total revenue is actually the area under the curve, and you will get much less. So that's something that we have to worry about. The other design metrics that we have to worry about is maintainability and of course correctness and safety, which we talked about. And there is always a tension between all these design metrics and as with any other product. So let's not worry about that. We already looked at this. So the other design considerations are dependability. So the reliability is the probability of the system working after a certain time, and this kind of systems usually age, the processor and the silicon ages, and then they have this normal wear and tear. And then also if the environment is difficult, like if you cannot do proper heat dissipation and so on, you can actually break your system. And maintainability, which is once you have an error, how you can fix it. So if you cannot fix the system easily, then you have a problem, right? So that's something you have to worry about. So nowadays the other big issue is security, right? So security is coming up as a big issue. For example, if your cell phone, if you don't have security, then others can hear what you are saying. But bigger problem is that when your bank is sending you OTP, then if somebody can snoop that OTP, your bank account may be compromised. So you have to worry about security all the time. Nowadays there is another thing about embedded system which I haven't mentioned yet, which is the IoT or the Internet of Things, right? So in the IoT space, we are talking about medical applications in IoT. So for example, patients might have various embedded sensors on the body, and then it can measure your blood sugar, your blood pressure, your temperature, and all that, and then actuate some other equipments on your body, for example, to pump insulin. Now, if somebody hacks into this system, because these are basically having microcontrollers of very, very small size, if somebody hacks into this system, they can kill you by injecting this thing. So same thing with the pacemaker. So and this happened in 2008, 2004 during the presidential election in the US. there was a story that Dick Cheney, who was the vice president at that time, he had a pacemaker, and there was a story about people might be hacking into his pacemaker to give him a his heart a high dose of shock. And so but these are real concerns, right? So people have been working on these issues. The about medical embedded system space security is a big issue, but also in cyber physical system where the security is a big issue. Like for example, if you can do a cyber attack on the control center in the load dispatch center, you can actually collapse the whole power grid, right? So these are important issues. So there are many now when you are designing embedded system. So there are many things that can go wrong, and some of the examples. So there are some very interesting examples. So one most well quoted example from the 80s is the story of Therac 25, which was a radiation machine for cancer patients, and it was an embedded system with when you change the settings, it will basically change the radiation intensity to cancer patients, and this had a malfunction, and it gave lethal dosage of radiation and killed a couple of patients, right? So this is a very well cited example of a malfunction of the software system in an embedded system. Here is an example of a failure of a Patriot missile during the Gulf War, the first Gulf War, and this was due to a precision problem that was in the computation, and this precision accumulated to so that the interception of a Scud missile by the Patriot was about 500 centimeter away, and this was not supposed to happen. This is just the arithmetic error that happened in the system, and there are many such examples. So there are examples where one engineer, a system was designed by two engineers. One engineer thought it was the pound and feet is the measurement, and another was in the metric system. When they interfaced the system didn't work, and it destroyed something. So this kind of things can happen in an embedded system. So operating environment, we already talked about you have to be rugged to various kinds of operating extremes, especially electromagnetic interference. Now real time, so real time is a big issue for most of the safety critical systems. So let's look at this more closely. So there are three kinds of real time requirements, right? So one is called a hard real time. Hard real time is that if you miss the deadline, it's not acceptable. For example, if you are pressing a brake, and if you are not responding within so many milliseconds, the system doesn't respond, then it is not acceptable, because any later you will basically create a disaster, right? So these are usually in safety critical system you see most of the hard deadlines. Now then there is firm deadline, where it is sort of like you want to make sure that the deadlines are met, but if statistically a few of them misses, it's okay. For example, if you are playing a multimedia system, if you miss a few frames here and there, you might be annoyed, but it's not going to create a disaster, right? So that's a firm real time. Then you have soft real time, when if you don't make the deadline, it is still okay, and the utility of making it after the deadline is not zero. It still can be useful. For example, a network switch or a router, where you have packets coming in, you want to send the packets as soon as possible and within certain deadline, but if you don't, then it will not be a disaster. So normally we represent this like this. So normally these real-time systems usually are systems where a repetitive task is being scheduled on a real-time operating system. So what happens is that so you, for example, you are getting video frames, and you want to process the frames, and then you want to send it to the next piece of system, and you want to do this as soon as the frame comes, you have to do this. As soon as the frame comes, you have to do this. So it's a repetitive task. And for each repetitive task, you kind of know when the task is going to be starting to execute. It's usually periodic, and then you have deadlines, right? So this, because the deadline is a function of the application. Like, you know, if for video processing, for example, if you are going to have a video of 24 frames per second, then you know 1/24 would be your deadline, your absolute deadline. So once you have the deadline, then you have multiple different of these periodic tasks in your hand, and your scheduler has to schedule them in such a way so that all of them can make the deadline, or at least the ones which have hard deadline should be able to make the deadline. Maybe the others may not be able to make the deadline. So that's the whole theory of real-time scheduling is all about, and that's a large part of your embedded system curriculum usually, the real-time system and real-time scheduling. And so here is just a simple picture that shows, you know, what is soft, hard, and firm deadline. So in hard deadline, if you miss the deadline, so at this point you basically your profit or utility is negative, because, you know, you probably harm the system. Firm deadline is like, you know, your utility goes to 0, which means that, you know, if you don't make it, then don't do it, kind of thing. You can drop the frame. 1 or 2 frames dropped is not a big deal. And soft deadline means that even after the deadline, you can still do it because there is some utility. It goes down as time passes, but at least it is you know, worth doing it after that. So that's all we are going to say about real time. You know, obviously it's a very big subject, real time operating system and real time scheduling, and this is also an area of research, because nowadays even in embedded space we are talking about multiprocessor or multi-core processors, right? So even in embedded, manufacturers are actually giving us multi-core processors. So now the question is, as it is, you know, scheduling real-time tasks on single processor is a hard problem, and now we are talking about multi-core processors, and so we have to schedule now on multi-core processors. Otherwise, we are underutilizing our processor, and if you are paying for the processor, we must utilize the processor. So this is an area of research that goes on even now. So levels of so the next thing is about system design. You know, what is involved in system design. So you already understood probably by now that, you know, you have to have a requirements, and you have to have a spec, and then you have to design an architecture, then you have to design each of the component, and then you have to integrate the system. So this is not something. So normally the way it happens in the industry is that you don't go like this, right? So this is the academic view of the system, that, you know, from requirements you will actually generate all of these. So normally you decide on the hardware based on other considerations, including availability, cost, and power budget, and things like that. Then and also your data path requirement, like, you know, if your data is only just some few control, you know, then you may want a 4-bit microcontroller. If your data is also actual data with voice data or video data, you may want a wider data path, like 32-bit, 64-bit data path. So the processor choice is often based on all these considerations, which is not following this requirements to implementation, you know, framework. And then once you have chosen the hardware, then you can either give a board in which you actually have the interface to all these different sensors and actuators, and the person developing software has to use this board to you know, fit on software on this board. But today, because now in the old days when you had this 4-8-bit microcontrollers, you know, you could do this, right? So nowadays when we teach you know, microcontroller course, we usually use 32-bit controller, right? So things have become very different. When we were students, we were given training on 8-bit controllers, right? So systems are becoming more and more complex, and you know, So it's harder to think of the total design at one go. So you might actually modularize your design, that this part does this part does this, and then you have to design the interface. Fixing bugs is difficult because it can be distributed all over the system, and an effect might be actually felt in one part, and it is harder to maintain because of its complexity, and so the traditional development process has to change. So this is design methodology for safety critical embedded systems is and also constraint, power constraint, area constraint, and latency constraint systems is actually an area of research, right? So so this is talking about development cycles, so we'll not worry too much about that. So one the approach that people are advocating nowadays is to do something very abstract, right? So, and this basically comes from mostly from Europe. So the American way was what we were discussing before, right? So you take the processor, you choose the processor based on all the market and other constraints, you build the board, then you build the software, and then it usually works because it was simple. Now because of this large complexity, you have to start at a higher abstraction level, and then you have to actually design in abstraction as much as possible. So you basically take the requirements, you build a very abstract model, and then when you build the abstract model, you basically decide, okay, so what we call a system level model, and then in system level model you actually delegate the different functionality to the different parts, and then you do a system level simulation. And with the system level simulation, you kind of get guaranteed, sort of convince yourself that if I have distributed these different activities to these different parts, they will work together. But you don't have the detailed engineering yet. Then you have to refine the design to a lower and lower level, and at some point you have to decide what is called a hardware software partitioning, what goes into hardware, what goes into software. And then you have to choose the processor that can make, depending on how much you want to delegate into hardware. If you want to delegate a lot into the hardware, then you do one thing, and if you want to delegate a lot to software, you have to choose a much more general purpose processor. So all this process, and then you have to automate the verification process as well. Now I don't think I have a lot of time here, so I have to probably finish up. So I will give the slides to you, and you can post, so there may be some more discussion. So I think I will just okay. So let's make this the end of this. So the disciplines that are used in embedded system design. So if you want to actually do a good training and research in embedded system, you have all these different areas that needs to converge, right? So VLSI design is one, parallel and distributed system design is another. Many of the problems are actually, nowadays embedded system is usually quite distributed, and network systems, real-time system, of course you have to understand software engineering, programming languages and compilers, and then you have to understand the application domain as well, right? So depending on what it is, the power system or automotive or music or whatever. So let's not worry about this. Now let's say future of embedded systems. So one of the biggest thing nowadays people are talking about is IoT, right? So Internet of Things, basically embedded systems connected by network, and then but bigger issue is that the amount of knowledge that gets floated up because of all this, right? And use that knowledge to do better control of systems and better utilization of resources and so on. So that's the one of the future of an embedded system. And then we are talking about smart home, smart city, smart transportation. All these things are actually basically outgrowth of embedded system as a discipline, and therefore all these things are going to play an important role in the future of embedded system. So I think I'll take questions if there is any. And thank you.